Let's do some AI research with AI, where large language models are doing AI research with me. And we will understand everything they do and learn from this. So since humans are too slow at doing AI research, and when AI can do something, it can do a lot faster than humans. I think we need to do LLM AI researcher. Or AI, I should say AI researcher, AI that researches AI. The way I imagine this is this will start to automate a lot of the things humans do manually. For example, what's not gonna get automated is this general intuition or feeling or taste for research that is very hard to for LLMs. But they can code, they can manage files, they can do some research from read PDFs and stuff. They can structure code bases as well. Now that I'm talking about it, they are very good at coding, structuring, managing code bases, and maybe explaining and writing. And then humans would still think what kind of AI research do they want the AI to do. Because for that you need a lot more context and maybe experience in this intuitive thinking. So it's gonna be most difficult for LLMs to replace that. Here I have my own LLM large language model that you can find on my channel in a bunch of videos. I want to do some research, I want to generate new knowledge. So I have this rotary positional embeddings, and I think this could be implemented faster in Triton or even Python, but probably in Triton code. So let's try to do that. I told my AI to just write another implementation, which is gonna be this RoPE kernel in Triton, and now I wanna test it with this. So accept. So this coder IDE, it just cannot fix these issues, it seems. But if I use Gemini code, it actually worked. So here we have results. We have batch size, head dimension. We'll see what this is, but the implementation is actually in Triton is faster by 1.6 times, 1.7 times, 1.4 times. And as we go higher, L here, it looks like it's getting the speed up is actually now PyTorch is faster for some reason. So I'll just copy this and see what Gemini thinks about it. Most important thing is that we understand every step that's happening. Don't get lazy. So I told it to explain this in README file and suggest research. I just wanna keep track of what's happening. This is the code. I will tell it to explain the code to me, but let's maybe try to do some more experiments. Most of the code is benchmarks, so from here it's like it's more than half, which is good. It means there is not too much to understand for us. The report from the experiment, the Triton kernel shows a promising speedup up to 1.73 for configurations with a smaller head dimension, 64. However, it's significantly slower than the PyTorch version for large head dimensions. This suggests that it's not fully optimized and might have memory access issues. But the Triton version does have half of the peak memory, so it just uses half there, so that's good. So half the memory, which allows us to use a bigger batch size, for example, or other parameters to take more memory. I told it to create more RoPE variations where we will test these more different implementations. It's very important not to get lazy and follow everything that's happening. I'm not gonna be understanding the code yet because it is a bit too complex, but I will run multiple tests, and once we finish testing all of the RoPE mechanisms and testing the best RoPE versus our current implementation that I have currently in my LLM, then I'm gonna understand the code for the best RoPE mechanism. So this is the report for the second one. Looks like our version 2, whatever that is a clear winner. Look at this. Look at this difference. This version 1 is worse than PyTorch, but version 2 is absolute winner here. So in version 1 we used what's called 3D grid launch. We'll learn more about grid launches later, but that was not efficient. But the 2D grid and 1D blocking approach on version 2 is a much more effective way to parallelize the RoPE computation. This is insane. This is 7 times faster here. Here, for example, it's just 2 times faster. You see how different shapes of matrices have huge influence on the speed, but anyways, this always wins 4 or 5 times faster to 2 times faster everywhere. Now I wanted to actually try even a few more of these versions to find the best one. Let's see the results of the new test. Looks like the version 2 still dominates. But version 4 is almost the same or same, it's just FP32. Now I want to benchmark the current one we have versus V2 and V4. Interestingly, Gemini claims that my implementation of LLM has a bug, my implementation of RoPE, but it outperforms his supposedly bug-fixed implementations, so has a better loss accuracy and perplexity. And it's so stubborn that it says committing the bug, so now it says like it's writing the same bug as me. Doesn't want to admit. My final experiment has Triton kernels performing faster, but validation loss is a bit worse and accuracy. So now we will just learn how to code this kernel, and we will probably learn how it makes the mistake. So our function starts with Triton just in time, and I'm just gonna let you take a look at the function, and then we will go line by line. So this is where we define the function RoPE forward kernel version 4. X pointer, out pointer, cosine pointer, and sine pointer. These are points to the memory locations of the input tensor X output and the pre-computed cosine and sine tensors. Triton kernels operate directly on memory pointers. Then we have stride. So stride X batch, stride X head, sequence and dimension. So for these. Then we also have batch out sequence and dimension for output tensor. Cosine we just have sequence and dimension, and for sine just sequence and dimension. These parameters represent the strides of the tensor. A stride tells us how many elements we need to jump in memory to get to the next element along a given dimension. For example, stride X batch tells us it just says how many elements you have of this thing in the memory. So if you have beginning, the pointer to the beginning of the patch, stride will tell you how much is the first batch, okay? If you have beginning of the dimension, stride will tell you how much is the first dimension. And so one batch will be the entire thing, like all of the dimensions, all the heads, everything. So stride is one of those things. Then this number of heads, sequence length, and head dimension are const expression. So they are just numbers, constant numbers that we get in the function. They are always same, so they don't change within this Triton kernel. So Triton can optimize a lot more because it knows which numbers these will be. So it can unroll loops and do other good optimizations. Block size D is the amount of elements we will process in this head dimension. So because head dimension is innermost dimension, then this block size D will literally tell us how many elements we will process at once, or how we will divide this entire thing. Because when we divide heads, they are innermost dimension, so we divide everything else, that means. Then we have a grid of parallel programs. It's a 2D grid. Each program will run parallelly, and each will compute its own part of the tensor, the matrix. So we get, for each of the programs, it has two coordinates. You can say first coordinate PID, I guess this is batch head, so the head in the row, and then S is sequence number. Triton launches a grid of parallel program instances to run on the GPU. TL program ID axis 0 or 1 gives us the unique ID of the current program instance along a given axis of the grid. In our case, we launch a 2D grid. We can have 1D, we tried with 3D, I think it didn't work as good as 2D. PID BH is the ID for the first dimension, which we use to represent the batch and head dimensions. And PID S is the ID for the second dimension, which we use to represent the sequence length. Then we will separate BH into batch and head. Here we are demultiplexing the PID BH into the PID batch and PID head. We are essentially flattening the batch and head dimensions into a single dimension for the grid, and then recovering the individual indices inside the kernel. This is common technique in GPU programming. Let's see examples to understand easier. If we have BH to be 0, integer division is 0 and division remainder is 0, so it's first batch and first head. Okay, BH7, this is gonna be first batch again, but 7th, or in this case 8th head, because first head is 0. So if we have 8, then you see the logic. Now this is the first batch, but within that, second batch with index 1, but within that batch we have the first head with index 0. So now you see how this works. Now we can calculate memory locations. Now let's see, we have stride x dimension 1, which means that to get from the first element in the dimension to the next element in the dimension in memory, we just need to move by 1. But for the first element in the sequence to the first element in next sequence, we need to move 64 elements in the memory, from beginning of one sequence to beginning to the next sequence. And for head, we need to move this many, and for batch, we need to move this many elements in the memory, from beginning of one to the next one. It also says how many elements are in one batch. So you need to move all of those elements in that one batch to get to the next batch. So that's this stride for each of them. Let's see some example with PID BH9 and sequence is 5. So this is sequence at index 5 and this is 9. So here we can get first batch with index 1, and then that's gonna be second head that is index 1, and sequence within that head has index 5. So let's see where this particular element begins in the memory. So we start from the beginning of our tensor, and then we go the full batch, because this is second batch, so we need to go like skip one batch, and then we need to skip one. This is second skip one head, and then skip, so we need to just skip 5 sequences, 0 1 2 3 4. So here the memory location is gonna be from the beginning and moving 74,000 elements. That's where this particular program needs to start to take the elements. So when each program has its starting memory position, then we need to have ID for each of the elements in that program. So starting from 0, which will be that starting from position. This means first element of this block to the block size. So this will just create an array of indices starting from 0 to block size. And later we will just take those indices and we will add the beginning position. So if indices are from 0 to 10, we add beginning position, let's say 70,000 something 4. So then it will be from this position to 10 plus this plus 10, each index. That's how for each block we will know exactly what its indices are in the memory by just adding the offset at the beginning of that block. We'll see on an example. So this will go from 0 to block size -1 because this is exclusive. Half D is half of head dimension. RoPE works by pairing up elements of the head dimension, so we only need to iterate up to half D. The mask is crucial for safety, memory safety. So if we divide into blocks, if the last block has some elements outside of the entire tensor, then those elements will be masked. They will not be read from the memory. They will just be replaced with 0. Default is 0. So the last block size of elements will have whatever is left, and the other ones are going to be replaced with 0. But usually you would ensure that the whole tensor is divisible by block size, so there is no extra elements. Let's see some example. If head dimension is 64 and block size is 64, then first half of the head dimension will be 32. Our offsets, our array of indices within this head will be 0 to 63. And now I see how this is programmed. So here we just need half of the numbers of the indices. We just need to load half. So you see we have 64 in total, but we will have true only for the first 32 elements. And we'll see why, and false, so we are not going to load the other 32 elements. So our offset indices are actually just 32 elements, and even though the whole block is 64, this is because we will divide the block into two separate variables. X1 will be all of the numbers in the first half of the block, and X2 in the second half of the block, because we have this starting from the second half. And so 32 here, 32 here. X1 loading half, X2 load half, load cosine and sine, which are pre-computed. TL load is the Triton instruction to load data from memory DRAM into GPU's fast SRAM. And we decided to cast to float 32 to maintain precision. The RoPE calculation is first part times cosine plus second part times sine. This looks like just a rotation matrix. So we have a vector which we divide into half, and then, this is just rotation matrix. This is formula for rotation matrix. You can learn more about it by asking ChatGPT or watching YouTube tutorials. It just rotates this vector. This is the core logic of RoPE rotation. It's simple element-wise multiplication and addition on the blocks of data we just loaded. This is the Buggy, but better performing version of the rotation. No, I don't think it's Buggy. And then we will just store that data. So first half stored here, y1, second half stored also, but we just offset by half here. And you know that these offsets are, so out base, this is where the entire out vector starts. Offsets is the chunk for this particular program, and is divided in half. So first half, second half. So TL will write from SRAM back to output tensor in DRAM. And mask is just to prevent writing outside of the valid memory region. We also have how the kernel is launched. It's just this grid. So one dimension is batch size times number of heads. So that's how many we have here. Batch size 8, number of heads 8, so 64 in total. And sequence length is the second dimension. I wonder if 2D, if 1D grid would work better. Probably not, but I'm not sure. I'm not sure what the difference will be here. Maybe this is something to learn next. So if we just multiplied all three of these, and then when we pick PID up here, we don't pick two PIDs, we just pick one. So they're just 0. And then we need to divide here better. And then we launch the kernel with this grid. This is an example. If we have batch size 2, number of heads 8, sequence length 128, head dimension 64. So the first will be 2 times 8, this is the first dimension. The other is the sequence length. So in total there is this many parallel programs in total. And the first one has dimensions. So it can be from 0 to 15, and the second program has dimensions from 0 to 127. I asked Gemini why it called my implementation Buggy. It explained here. I didn't really understand it, but if you want, you can read, maybe even explain in comments. There is also this entire README that explains it a little bit. And that's kinda it. Check out other videos on my channel. And you can support me, help me buy more compute, and help me do this full-time so I don't need to get a job. I just want to do research full-time, post everything on YouTube, and that's it.